Hello, welcome to my project presentation on using physics-informed neural networks to determine the wave functions of electrons in molecules and atoms. Physics-informed neural networks, or PINs, are a new method that can be used to approximate the solutions to partial differential equations, or PDEs. They can also be used to generate those PDEs from the data that has been gathered empirically. This PDE must take the form of the equation shown on the right, with U as the latent solution that is unknown to be determined, and N is a nonlinear differential operator. One benefit of this method is that it doesn't require labeled data. However, it does require specifying the initial and boundary conditions which will be enforced at selected points. The reason why PINs are being developed is that they can provide solutions to equations with no known analytical solutions. An example network diagram is shown in the upper right. In this example, the PIN is split into two parts, a fully connected feed-forward neural network on the left, which produces the unknown solution U, which is then used as the input into the differential equation, which gives the result F, used in the loss equations shown underneath. The main aim of this project involves solving the Schrödinger equation for different molecules. This is a PDE that governs the behavior of quantum particles and has been substituted into the previous PIN equation from the previous slide. The solution to this is known as the wave function, which is a mathematical description of the quantum state. For electrons around an atom, a simplification can be made to give the time-independent Schrödinger equation, for which the wave function doesn't change over time. This is shown on the right, with the potential and kinetic energy of the electron being included in the Hamiltonian operator H. This equation can be solved for hydrogen to give an exact solution, but for larger atoms there is no such solution. This is why a PIN would be useful in approximating the wave function, as there is no solution. Next, the network architecture that was used was based on a method that was developed to get a neural wave function and a neural energy approximation for an electron around the H2 hydrogen ion. It takes the two inputs. One is the position of the electron, the small r, and the second is a large R that encodes the geometrical setup with the two atoms, so that it describes the distance between the two atoms. The solution is guided by first approximating the solution using the linear combination of atomic orbital approximation, which uses hydrogen atomic orbitals for each of the atoms. It also contains three feed-forward neural networks. There is the basis unit, which corrects the linear combination. There is the gate, which learns the range for which R, where the output of the basis unit B is important. And the energy unit, which only requires R, as the energy calculation does not require the position of the electrons. And this can be, the basis and gate unit can be frozen, so the energy unit can be fine-tuned after the main training has been complete. The first thing that had to be changed about this is that the linear combination approximation for the molecules will have multiple atoms and therefore multiple atomic orbitals as well. On the left is the linear combination wave function, which sums all the hydrogen atomic orbitals that can be occupied in each of the atoms. Each atomic orbital is multiplied by a constant c, which needs to be determined. Below that is the Hamiltonian for one of the molecular orbitals, with the first term being the kinetic energy of the electron, and the second term being the potential caused by the effective charge of each nucleus. The only problem here is calculating the constants c for each molecular orbital. They can be determined by forming the Ruthin equations that are being shown in the center, which are a set of n equations of n orbitals that are created using the time-independent Schrödinger equation. These can be rearranged below to give an eigenvalue problem, where the eigenvectors each contain the n coefficients of c for each n possible molecular orbital. So each of the eigenvectors corresponds to a different molecular orbital. And these molecular orbitals come in different types that are similar to the sp, d, and f atomic orbitals, and they are known as the sigma, pi, delta, and phi molecular orbitals. Learning the shape of these molecular orbitals in molecules and how they interact together is important as they determine many of the chemical properties that we see. On the right is an example of two sigma orbitals that can form between hydrogen atoms. The left is the bonding orbital, which increases electron density between the atoms, and on the right is the anti-bonding orbital, which decreases electron density. In the bond of H2 gas, the two electrons fill the sigma bond of lowest energy, which is the bonding orbital. Next, the results for H2 were determined. These were chosen because to recreate the results of the original paper that this network was based on. However, as you can see from the left graph, the neural wave function resembles the sigma bond, which is expected. However, it exactly matches it, which was not how it functioned in originally, which suggests the network might be overfitting towards the linear combination approximation rather than learning the solution from the differential equation. When analysing the error of the neural energy on the right, there is a much larger difference with the ground truth than in the original paper. There weren't many changes made to the energy unit as I was mainly concerned with the wave function during the development. So it's unclear what change caused the increase in error. One reason might be that there wasn't enough training performed during the fine-tuning phase, or the lowered number of training points may have caused inaccuracies. Next, the pin was used on a larger bond in the oxygen O2 gas. This was chosen as it should feature a pi bond. On the left, you can see a 3D plot showing the value of the wave function along a 2D plane of space. This is one of the resulting molecular orbitals that I was able to produce, and it resembles a sigma antibonding orbital between two of the p orbitals in the oxygen atoms. However, it was difficult to produce the other molecular orbitals due to a number of different reasons. There were many limitations that became apparent in the development process. Most notably, there were hardware constraints on memory that meant the training size had to be reduced and the compute time drastically increased. This is why results weren't able to be achieved for the free atom setup as originally intended. The extra set of polar coordinates took up much more space, and the only way to reduce the size was to reduce the number of training points being used, and this only made the results more inaccurate. There was also no way to select the molecular orbital being calculated in advance, which means as a result, it had to go through the whole training process without knowing what the resulting molecular orbital was going to be produced in the end. Okay, these results definitely don't show that the pin developed in this project needs some work if it's going to be useful for approximating wave functions. Even then, it is still limited by the hardware I was using, and most importantly, doesn't include electron-to-electron repulsion, which was originally going to be included in the Hamiltonian. And this is important as electron repulsion has a significant effect on the molecular structure. One thing I have concluded, though, is that the method of calculating molecular orbital wave functions drastically increases with the number of atomic orbitals present. And so it might not necessarily be a better alternative than Hartree-Fock or density functional theory methods if the compute time is so large that it's difficult to calculate large atoms. So this concludes my presentation. I hope you enjoyed.